All right. So I think we get started. Yeah. Works. Okay. Yeah. So want to continue where I stopped. So that's on the GKP code. And as promised, we'll talk about the cat code, bias noise, and I'd like to discuss a very recent paper. And then, if I have some time, I'll touch on another qubit, a dual rail qubit. So all these qubits are sort of under construction, and it's not clear, like, you know, who's going to be the best, sort of, in the end. This is going to be a best. Okay, so I introduced the GKP code, which had these two stabilizers, SP and SQ, but it was clear that the sum of delta function peaks is not very physical, so we need to look at how to prepare states with finite energy, and for example, there's such a state. And you could get some intuition, because you could say, well, maybe I need to, if I have a squeezed vacuum state, it's something that is, you know, compared to a squeezed, to a normal vacuum, it is a bit of an eigenstate of SQ, right? Because it has, you know, it's very focused at Q is 0. And so that maybe is a good starting point, because I need to be sort of a +1 eigenstate of SP and SQ. And so I'm starting with a state, the squeezed vacuum. And so the noise in the Q quadrature should be reduced to something small. That is already good for SQ. So and then I'd like to become an eigenstate of SP. Now just one, I think it's this one, just for your information, the squeeze states. So this is the Wigner function of a squeeze state. You see it doesn't, you know, it's sort of, you know, thinner in one direction and more spread out in the other direction. And it has this, it obeys the sort of Heisenberg uncertainty that the sort of, you know, the variance in the product of the variances of both quadratures should be lower bounded. This is like a squeezed vacuum or something like this. Yeah, and of course I can change by changing, you know, psi, I can change in what direction I squeeze. So that's a little bit on squeezed. So that is a component that's often, you know, present in optics for sure. But you can also do it in the microwave regime. But we'll come back to that. All right. So now, so one idea, now you could say, well, if I squeeze, then let's say at 0, I already have this peak in the middle. So what should I do to get the peaks on the side? I should be sort of, you know, going into a superposition of displacement to the left and to the right. And if I do this sort of repeatedly, so this is displacement, now this is not left or right, this is, you know, identity and, you know, one to the left or whatever right. But of course I could apply, you know, half the inverse in front, and then it's symmetric around 0. So if I could repeatedly apply this operation, which is of course not unitary, to 0, I would get some Gaussian envelope, right? Because I'd get something where I say, okay, so, you know, if I do this repeatedly, the number of times I apply SP squared would be, you know, n choose 2, right? Because if I apply this n times. So I'd get some kind of, so I say identity SP, identity SP, identity SP, etc. And so I would, you know, I get this distribution would be sort of like a Pascal triangle. So I get a binomial distribution, and binomials are sort of approximately Gaussians. So that gives you some intuition that what I should be doing is applying this. Now, I just want to mention some other, so there are many approximations for analytical ways of writing an approximate GKP state. And they're not all the same, because, you know, there's a lot of possibilities, of course, because it's a large Hilbert space. One thing that we'll refer to is this approximation where it's sort of simple, because I have a perfect GKP state and then I sort of have an envelope. And this envelope is characterized by some squeezing parameter delta. And you can really think about that this state, you know, kind of realizes squeezing in P and Q by this delta in some sense. So there's a... Okay, so and I can say, well, if I repeatedly apply this at some point, you know, how many times do I have to do this in order to achieve some delta? Now, of course, the state I'm getting exactly is not of this form, of course. There are all kinds of approximations. Yes.
Sorry, the SP is a stabilizer of the whole.
Right, yes.
So normally, if I have something like identity plus SP by 2, I would think of it as a projection on.
Right, yes.
So is it correct to think of it that way?
Yeah, and in some sense, but that, as you're saying, it's not, the eigenvalues are, so if I am in the code space, it doesn't do anything, indeed, that's the point, yeah? And, but if I'm outside the code space, it has a different, different action. Yeah, you can also see it as if I multiply with SP, SP a half inverse, it's sort of like a cosine, right? Because cosine of this argument in SP. And you can, yeah, yes. Oh, okay, sorry, this in the back, yeah, sorry.
The perfect DKP state has infinite energy, right?
Yes.
So it's not normalized.
Yes.
But then if I do this approximation, this is a normalized state.
Yes. Yeah. Yeah. Of course, this is, I haven't put in a normalization, but you can, it is a normalized state. There is a nice paper of 3 Japanese authors where they compare all kinds of approximation normalizations, which actually involve theta functions and quite sort of involved math. Yeah. Your question, sorry. What would be an eigenstate of SP?
Eigenvalue.
An eigenvalue, well, SP is a unitary operator, so the eigenvalues are phases in general, right? And so that's why if I imply SP inverse, and this is sort of like SP to the, this is SP to the half, and this is SP to the minus half, I get a cosine, and I get a cosine of that phase, right? So this is sort of the, see, as the cosine operator is also a sine operator. Okay, but let's look at, now this is, okay, so what I'm now explaining is one way of preparing the state, but I also want to tell you what they actually do in the experiment, or approximately tell you the experiment. This was an idea that I had with my student to sort of do this, and it was partially done, but then other methods that were better came around as well. All right, so one way of preparing a GKP state is, let's say we want to prepare the 0. And so, so we start with a squeezed vacuum. So your Q is centered around sort of 0. And then we apply control. So we have a qubit. So this is a storage cavity. We have a qubit, which you put in plus. And then we need to do this operation controlled displacement. This is going to be a very central element. You've already seen that you can, if you have a qubit and there's a cavity mode, you can do controlled rotation because of the dispersive interaction, right? And the controlled displacement is something that we haven't discussed. Now, if you have trapped ion qubits, that actually is fairly natural to do. But for the superconducting systems, you have to come up with some scheme, and I'm discussing this. All right, so why do we want to do this? So, okay, so here in this little circuit, I say I want to do controlled. So here, for example, this controlled displacement is just controlled SP, right? Now here I said also, because I want to symmetrize things, I want to sort of do SP to the minus a half in front, right? So I can sort of go both ways. Now, in principle, I could also do some additional single qubit rotation and then measure in the plus minus spaces. And the claim is that, for example, if I were to run this circuit, and I say this phase is 0, when you measure this qubit, when you measure it in, say, 0, or, well, actually I measure plus minus, that I will apply this kind of thing to the state. So there is this first, this, you know, unconditional displacement. Let's sort of ignore this. But what I do is I apply, you know, the displacement plus or minus the identity. So then you say, oh, well, I want to, you know, you told me I want to apply this with the plus sign. So I have to post-select on this. If I sort of maybe repeat this round, I should post-select on this qubit coming out a certain way, right? But this is sort of too negative, because basically what this kind of circuit does, if I repeat it, this is sort of a phase estimation circuit. If you're familiar with quantum algorithms, if you look at, if I say I have some unitary U and I have to estimate, like I'm not an eigenstate, or maybe I am an eigenstate and I want to estimate his eigenvalue, then what I should do some, well, qubit controlled U to decay. But actually I could just also do controlled U. So the point is that if I have my storage cavity, I have a qubit around, I do this controlled displacement, I measure, I have another qubit, do it again, etc., etc. What I'll be doing is I'll be projecting my storage cavity onto an eigenstate of this unitary operator, approximately, and I'll be learning an eigenvalue. Because, you know, basically what this operator does, it's learning information about the eigenvalue, therefore it's doing the projection, right? So now I don't want to use necessarily control to some power of this displacement. I could, but you know, it's more costly, so we may not want to do this. So we came up with a scheme where we showed this also numerically. We show if you do this kind of circuit and you measure these qubits, you'll be projecting approximately this into a state, into an eigenstate of SP. And of course, we don't need a perfect eigenstate because we want to have some approximation. But the approximation we get looks good. And I don't have to post-select on this because actually what this information gives you is information about the eigenvalue phase, right? So you can, now in experiments, actually what they do, for example, in the first experiments on this GKP preparation, they did a little circuit like that. And then depending on this one bit of information, they do a little displacement on the storage cavity. You know, you get one bit of information and that sort of gives you, like, well, oh, maybe I should push the state this way or that way. And then they do a sequence of these things. And that provided the stabilization or, I'm actually not, the review that I've written covers that a little bit, but I'm not gonna cover this, like how this is done exactly. Okay, another way, of course, is say instead of having the squeezed vacuum state, you could start just in the vacuum and then you could run a circuit like this for SP and you could run one for SQ and repeat them, you know, alternate them. Yeah, and what I said, you know, these other alternatives is you apply feedback. You could apply feedback. The first experiment, they applied feedback after such a round, but you could also apply feedback after a much more complex round. We'll come to a little bit. Yeah, so you adjust the state. Now, the thing I want to stress, and maybe I've already done that a little bit, is that anything that uses a control with a single qubit, when you measure that qubit, it's time consuming compared to typical gates that you do. At least it does like, you know, 500 nanoseconds because this is typically a transmol qubit, and you only get one bit of information. And that is really a little bit of the bottleneck, I think, of some of these schemes, that you're trying to, you know, stuff your state in a high space, so high dimensional space, so there's a lot of errors that can happen. But your control is through a qubit for which you get not a lot high data rate, sort of per unit time, so to say. Okay, so yeah, so now let's talk about, so I said controlled displacement. You know, no matter what we do in the experiment, controlled displacement is an important component. So I want to talk about that a little bit. Now, so when we thought about, okay, how we do controlled displacement, we wrote down this little circuit. So let's stare at this for a moment. So we have here the cavity mode. We have a qubit. And what this gate is a qubit controlled rotation. So this is of this type where I say is e to the I z a dagger a times t, and the t is this pi over 2. So that's some specific amount, some specific time. You know, the exact thing doesn't matter too much. Okay, but here and here I flip my qubit, and here I do so my goal is to do a controlled displacement for some value alpha. And I could, you know, and actually do this pre-displacement. I could read this as, you know, depending on my qubit being in, you know, z is 1 or minus 1, I do d minus alpha over 2 or d plus alpha over 2. Right? That's sort of this stuff. That's what I want to do. And And if I look now, we're going to take this apart. So if I do, for example, here I do a controlled rotation, and this controlled rotation, you know, this strength is one direction, right? The rotation, this chi, there's a chi here, and chi is not negative, chi is positive. So if I want to, maybe I want to run, you know, this in reverse. The way I can, of course, do this, I can conjugate, I can first flip my qubit, do the gate, and then flip my qubit again. Right? Because here, you know, I run in one direction if z is +1, I run in the other direction, rotate in the other direction if z is -1. So if I just flip my qubit, I can rotate in either direction. So what I have here, this little unit, is just rz pi/2. So basically what I have here, this is a conjugation of this displacement by an rz pi/2, right? Because now I have something that is like r minus z pi/2 di alpha, and then here I have rz pi/2. Right, so I rotate, and so maybe this is sort of, and this depends on my qubit. So let's say my qubit is z is 1, then basically this displacement, you know, I'm conjugating displacement by a rotation, so I'm just doing a displacement in a different direction. And that direction change is pi/2, so from I alpha, I go to, you know, alpha, or I don't know where alpha is. Okay, so it's a pi/2 rotation, so that's one way to do this. All right, but the point is that, okay, so this is not what they do in the experiment, because, well, we said maybe you need a tunable. So the problem is that in order to do this fast, so you need always this pi/2 rotation to go from alpha to I alpha. That's part of this operation. And actually the chi that does this rotation, you'd like to take very small. And I alluded to that in the yesterday, because actually if it's very large, it also comes with a Kerr term of the cavity mode, right? So, and I don't like that cavity to be nonlinear, so I like it to be small. But if it's small, let's say 50 kilohertz, and that is in one of these experiments, this is slow, right? So now you could say, well, maybe if I have a tunable coupler, meaning I could have a dispersive interaction that I can turn on and off. And that is actually something they do in this noise bias paper that I'll discuss. And that is not unheard of because, you know, this also happens between transmon qubits, sort of modern days, where you say, I want to do a ZZ interaction, but I don't want that interaction to be sort of on too much. And I use something called a tunable coupler, for which I use, you know, additional structures. Anyhow, so you say, well, it's off for a while and it's large and much larger than kilohertz, but more like megahertz or something when I need to do this gate. All right, but what they do in experiment is actually, or one in the experiment, this first GKP experiment by the Yale group was something more like this. And we can track, and it's kind of a very clever thing, because what it does is sort of use the fact. So if I look at this figure, it's something where you say, okay, I do, you know, if I'm in the, I have a state here, let's say a coherent state out here, or maybe it starts off here, in there. And of course, depending on, you know, whether I'm in the ground state or excited state for my transmon qubit, I rotate this way or that way. And it's clearly also the case that, of course, the further out the state is, the larger the effect of the rotation, right? So what I want to do to enhance the effect, I sort of want to do I want to, you know, move my state to a state with a lot of photons and then do rotations, because then they do kind of big stuff in phase space, right? And so my GKP is sort of like here in phase space, but I want to move it, they actually move it to like 50 photon state to do the rotations, for these rotations to have a bigger effect. And this is sort of demonstrated here, and this is, you know, the scheme is here. So in this picture, I start with the vacuum state, and it's a squeezed vacuum. And first it's displaced by d alpha. So this doesn't depend on the qubit, and that's this point. This is what I do on my qubit. Then I wait for a while. And during that time, this dispersive interaction with the qubit is happening. So depending on the qubit state being E or G, so G for 0 and E for excited, state 1, I rotate to the left or to the right. Okay, so that's those trajectories. Okay, what I do now is I do another displacement. This is the yellow line. So let's follow this trajectory. I go down. And at this point in time, I do a pi phase shift on my qubit, which flips, 0 to 1. So I interchange 0 to 1. So it means that, so I've rotated this way. I do a displacement. I continue with another displacement. So those are these two little things. They don't depend on the qubits, it's unconditional displacement. And now I'm here. And now my qubit state has flipped. So if I now just let it sort of idle again, I rotate in the other direction, right? So before I went in this direction, I go down, but now I rotate in this direction because I did this pi phase shift. And now I'm here, and now I do another displacement, and here I end up. So the point is now I've started here, and when my qubit was in the ground state, I ended up with here. And if my qubit was in, well, now, yeah, of course, it's got changed. In the end, there's a, if the qubit was in the other state, I ended up there, right? So there's these two trajectories where you go up and there you are, like there, you end up there. And in the other case, you go this way, you end up there. So you've done, for the squeezed vacuum, you've done a qubit conditional displacement to there and there. But the point is that you've done it with, that t over 2, this time that you do the rotation, can be sort of quite small. And maybe this is not entirely clear from this picture, but I thought this was quite a clever kind of scheme. But of course you say, well, if I push the state out to a very high photon number state, at that moment in time, I suffer more photon loss. So this shouldn't last too long, right? Now, another point of this slide is a little bit a point that is made and comes in later, but I'm not going to explain it, that actually it's been shown that if you say, I want to do any unitary on an oscillator and a qubit, I can do that by a sequence of controlled displacements. ECD is, I don't know what it stands for, controlled displacement. I don't know. Echo. Yeah, okay, so it's echo control. Maybe this is the echo. There's also some protection again in it. But you can do it with qubit rotations and then some controlled displacement. So this is so if you say, maybe I want to prepare a GKP state, not in this sort of like following a little circuit, but maybe in a more sort of numerically optimized way, by which I learn the circuit. If I have these types of components, in principle, I should be able to make any unitary. So that's handy. Any questions here? Getting hot. All right. All right. So now, so I want to introduce or briefly mention something that I'm actually not entirely expert on, but was proposed. So we had this idea about seeing this as phase estimation and doing this controlled displacement and so on. But then there was a very neat idea, and I think the basic one thing is nicely explained, is that I've introduced this envelope, right? This f of delta, which you can see any approximate GKP state or some approximate GKP state is applying that envelope on the perfect things. And you can also conjugate the two stabilizers in this way, and they still commute. Right? And so you can say, I want to prepare an eigenstate of these two operators, really, because I want to work with finite photon. That is actually a better perspective in some sense. Now, these are no longer unitary, right? So, but then you say, well, but it's true that the approximate state is a +1 eigenstate. This state is a +1 eigenstate of this, or at least that's the goal, right? Because I undo, this is just the inverse of this f. And so if it touches f, then and then SP, so that works, right? So I have something, have some operator, say call it A, for which the approximate eigenstate is this eigenstate. And then in this paper, they say, well, what we want is actually, we can relate this to some modular operator, let's call it A tilde, because it's not really, of course, if A on pi approximate is 0, then this is true, right? But the point is this has a modular structure. It could be a plus 2 pi, you know, it could have a I2 pi phase shift, and this still holds. So this is, if, you know, just asking that the psi approximate is annihilated by A is too strong. So they define some modular operator, and then you say, well, yeah, great, but how we're going to go about doing this? But then you have some, in principle, some Hamiltonian that you can come up with. So the idea is now, you say, I write a Hamiltonian, and that Hamiltonian is not just involve the oscillator, but some additional mode, and I want to engineer the dissipation, right? So this is the paradigm where I say, you know, maybe that additional mode is just a qubit, or it could be a real bath, and I want to control the interaction it has with the system, and I want that additional system, that qubit or that bath, to, you know, lose photons all over the place. But because the specific interaction I enforce, that drives my system to some steady state, which is where I want it to be, right? I want to set up some Lindblad equation such that the steady states are these approximate GKP states, say. And so the claim is that if you have some Hamiltonian like this, for example, for P, where this is now A tilde P is sort of this modular operator. I don't give you details here, but the idea is that, you know, for the approximate states, this is 0. And because this is 0, if you put that in this Lindblad equation, then you know, this will be 0 for these approximate states, right? Because and then, you know, so this type of states, the psi approximate, where psi approximate could be a 0 or a 1, you know, the whole subspace is stabilized. And vacuum for this additional mode is the steady state of a Lindblad equation. Now, you know, this is one sort of, you know, bit of quantum optics way of looking at it. Now, in an experiment, there is some kind of type of protocol that tries to realize this by the mode being realized by a qubit and by some interactions, and possibly also this qubit is measured and there's some feedback done, and then the qubit is reset to 0, right? So it's sort of, you know, so it's a little bit more complicated than this sort of basic picture. But I want to, you know, suggest this because I believe that in experiments, you know, they like this dissipative sort of engineering approach. But I mean, there are caveats, of course, because you say, well, you know, if it's on, I have to do all these interactions. So when am I going to do my gates, right? And I have to turn it off. Now, I shouldn't be turning it off too long, right? The other thing is that it has to be driving you to this stable manifold, like these states, you know, the 0, logical 0 and the logical 1, at a sufficiently high rate. Because, for example, you know, I'm in this stable, you know, this steady state of this Lindbladian. If I move out from 0 to some other state and I come back into 1, I make a logical error, right? So this is sort of an error correction mechanism that is not relying on you measuring data on the outside, right? Which is usually what we think about with error correction. But it is doing error suppression in some sense, right? Because the idea is if the rate at which you move out of this, say, for example, you're in a 0 and you get errors that sort of change your state, if you suppress those errors sufficiently fast, then you're likely to be moving back to close to 0 and not to 1. Okay, so this is, it's a different, I guess with this workshop in Bangalore that was happening was also more focused on this type of mechanism. And it's interesting to contrast this also with error correction, where we say everything is measured classically and then we have to decode and we correct errors, we use all that information. Whereas here in principle, well, if you measure through a qubit, you get information and you do feedback, but it may even be that, you know, in this type of picture, we don't even get any information on the outside. Yeah.
The rate at which you're stabilizing is related to kappa? Would kappa,
Sorry, what?
would kappa somehow...
Yeah, of course, there's also, I didn't put in a constant here, but that indeed, both these things play a role in how this stabilizes, yeah. Yeah, okay. I mean, this is a little bit sketchy what it does exactly. So just wanted to, you know, sort of mention it as a, yeah. All right. Now, okay, so if we talk about something as a qubit, like my GKP qubit, I also need to discuss, you know, how I do logic on it in principle, right? Now, one of the things that was critically asked when this GKP code came about was that, well, yeah, you said it could correct small shifts, these displacement, but what about photon loss? Because that's the dominant source of noise. And in principle, you can show that that it is also good at correcting photon loss. This is fairly theoretical result, so to say. But there is also this thing that in practice, you know, like the more you squeeze, so right, a perfect GKP has sort of delta to 0, right? So it's this infinite number of peaks. So the photon number diverges. And so you can imagine that that limit is both unphysical, but also not performing the best, because the effect of photon loss or maybe rotations will be large, because I'm you know, if I'm far out in phase space, those effects will not be small displacements. There'll be big movements in phase space. And that this paper actually doesn't express that very well, but there are other results more related to my previous slides. For example, in this paper by Royer and Singh and Gervin, which show that indeed, if you do this stabilization and you intersperse it with little photon loss, that going to very large N is not the right limit. You really should stay with, there's some sort of sweet spot region where, you know, it's you are the best at correcting photon loss. All right, so okay, so what about the other things? And you know, there's numerical studies, so usually this is just addressed numerically. How well can you correct errors? You just have to, you know, just try it out with some approximate states and so on. There's not much analytical things you can say, or at least I think it's limited. All right, so now we want to say, well, okay, so how we're doing error correction and so on. So this is something, in principle, because this is sort of a stabilizer code, we can do error correction using GKTs and Scillas. And nobody's done this experimentally, and why not? It's because, well, first of all, it requires a C0 between two GKP states, so between two oscillators. And this is not an easy component. We'll come to that in a moment. And secondly, it's not so hardware efficient. Like, it's not like a little transmon that I have on the side. No, I have a whole other cavity, which may also need to be stabilized by its own transmon and another readout resonator. But I do think that this is more likely to actually do well in practice. And this is something where, you know, this is usually called Steen error correction, where you say, if I have Z errors, they will be on my qubit, or, you know, encoded qubit, they will propagate through the C0 and they will be measured here. And if I have X errors, they will propagate here and I'll measure them there. Right, so this looks a little bit like, you know, sort of future, or I don't know what it will, whether it will be in future. But it also uses this sort of, you know, fault tolerant measurement of X and Z, which is the fault tolerant measurement of P and Q, which is also a bit of an issue how we do this. Now, what's done for the quantum error correction now so far is they should just, we stabilize it. Right, so no gates. Well, you can actually do gates like these single qubit gates, but you don't do this kind of thing. You just couple it to the qubit and you do this active stabilization mechanism. Okay, so the preparation of these states is certainly not as easy as for a transmon qubit, because we've seen that this requires other resources. Now, one reason why GKP, you know, was put forward partially is because gates like the Hadamard gate and the S gate, you remember S gate is on a qubit is identity I. Right, so what gates do I need on a qubit? I need the Hadamard gate, well, typically the Hadamard gate, the S gate, the T gate, and the C0 gate. That's a universal set of gates, so I can check with all of them whether I have them. The Hadamard gate is something that interchanges X and P. So here in this case, it interchanges Q and P. So that's just a phase space rotation. So that's very easy, or it's even, you don't need to do this. The S gate is something you can write like this, and it does, it's something you can obtain by squeezing. So the nice thing about these gates, these are, readily available. So this is just a phase shifter in optics, right? So and that's one of the sort of appeals. But now the C0 gate also looks like it's the easy gate, because again, if I look at transformations of boson, there are transformations that are linear, have a linear action on Q and P, right? They're usually called Gaussian. And so the point is that all these gates, C0, S, and Hadamard, are Gaussian operations for GKP. And that is attractive if you're doing optics, because beam splitting, squeezing, phase shifting are very easy components. So then in optics, the idea is, well, you have to just prepare the GKP state somehow. And that's where that's where you need non-Gaussian operations, or non-linear transformations of Q and P. Right? But that problem is not so readily solved. So you could say, well, okay, so the GKP qubit has an easy C0 gate. The way you can understand C0, you just have to look at how the logical operators of the code transform, right? And it turns out to be this. This is not so relevant. I'm just showing you this circuit. You can do it with something that is beam splitting and squeezing by some amount. But that doesn't mean that this is easy in microwave, superconducting microwave things. Because, well, it depends on how if you have two cavities, you have to have a beam splitter, and you'd like that beam splitter to be turned on and off. And, well, the Yale group, Sholkov, they have done such experiments, but it's something that is developed. It's not something that's readily available. I think squeezing is somewhat simpler, but okay. Now, another thing is that this, another way of seeing, so the control Z gate, for example, is actually generated by a Hamiltonian. That is QC times QT, and C stands for control and T stands for target. And if I write Q in terms of the bosonic operators, it's something that looks like this. And if you, just write it out in 4 terms, it has one term, which is beam splitting, because beam splitting is A dagger B plus A B dagger, right? So we have 2 modes. And 2-mode squeezing is where I have A B plus A dagger B dagger, right? Or, yeah. So, but the point is that this operation requires both at the same time of equal strength. Now, I could be trying to do this, but of course I could also run this type of circuit, right? It's not a unique thing. But I just want to point out that from theory perspective, you say, oh, this is linear optics, it's simple, blah, blah, blah. But from experimental perspective, that is slightly, you have to think differently. Because so the point is that for the GKP, other than what we heard by the speaker last week, the C0 gate has not been implemented. And what he mentions was they implemented by some numerically optimized protocol. They don't really try to do this interaction. They have some optimization that gives them, the gate, the 2-qubit gate they want. And so, this probably can be done. Maybe there are companies working on this, but it's not entirely trivial. Now, so if you want to know a little bit more about these mathematical transformations, for example, if you say, I want to verify that if I do this S gate, what does it do with P, right? Because if I know what it does with P in terms of conjugation, I also know what it does with SP and the logical X and so on. And you can just use these, commutators of commutators and so on, and use that at higher commutators and some point are 0, blah, blah, blah. So my review actually, yeah, I think you can check these things if you want to know. All right. So is there any question? Yeah, I was going to go to some experiment, but is there any question here? No? Okay. Yeah, so the first GKP experiment was that of Fluman in Nature on trapped ion qubits. And then there was a very nice experiment at Yale by Campagne-Ibark, which used these, these controlled displacements and then a little feedback in 2020. And then, but that experiment, because we used this transmon qubit, that experiment was suffering from, the transmon not maybe being the best transmon there is. Right, so that's this point of like, so in this experiment, so in 2022, they took a transmon which is of a different superconducting material, tantalum, and it had a very long coherence time. This is extremely long. And that really helped. You could say that's enabled this thing. I mean, that's of course a little bit kort door de bocht, as we say in Dutch. So that's a little bit, not capturing the complexity of the experiment. But I believe that this was a big factor in this thing being very successful. Because they got, so you have a cavity mode that has 610 microsecond T1, right? So it's a decay rate 1 over that. And then they got a lifetime of my qubit. Like if I prepare a logical plus and see how long it lives, it's of 2.2 milliseconds. So this beats, any of these numbers, right? By quite an amount. So this is beyond break even. But then you can, of course, say, well, what about logical gates? Is that also beyond break even? Is that comparable? And the point is that this is quite a complicated thing. So here I have a different type of cavity that you haven't seen before, and the transmon is sticking here in, and they actually, so there is a sort of what they call a QEC cycle, which is something that has multiple layers of controlled displacement and qubit rotations, which is to enable any unitary. And then at the end, it's something where the qubit is measured, reset to 0, and depending on the measured qubit, I do a correction. And this whole thing is like, say, and this again breaks down into actually, into some, well, this is one of these units that we've seen before. But this whole unit is sort of measuring SP. And we have to do that for SP and SQ. But they use also some reinforcement learning. They use some optimization. So they don't design this sort of on paper, but they use some optimization to get this. All right, so that I think for me concludes a little bit of the discussion of GKP qubits. Of course, we hope to see, it's just a matter of time perhaps to have more progress on this. But I do want to point out that if we do everything via transmon qubit, we do get little information. With transmon qubit, measurement takes time. A transmon qubit has its own limitations. And that is maybe a bit of a bottleneck in some sense. All right, any questions at this point before I move to cat qubits again?
So this one cycle of QC to prepare or to stabilize your qubit requires some n layers of this.
Yeah, this is quite complicated because they want it, because you say, well, why n layers? But that's because of this learning thing that they try to do.
But even in the protocol that you explained earlier, you have to keep repeating this I plus SP.
Yeah, but that's much simpler, right? Because then you say, well, you do control but this is this is more inspired by this Gervin et al. Work. But it was also not, I think, literally using, so in this Gervin et al. Work, there is some specific sequences that could implement this sort of stabilization map. And that's not exactly what they're using here. So they let it sort of optimize, because I guess the optimization also involves the particular types of noise sources that you have. Yeah, I'm not showing any, well, this is too fuzzy. Yeah. But of course, it shows a little bit that maybe if you really want to push the envelope, in-place optimization is better. But then, of course, this is not very scalable, right? You're not going to do this for every cube, you know, if you have many qubits. Yeah. And I also haven't seen, you know, these big cavities, well, these 3D cavities, I haven't seen experiment where they have many of them and many, you know, bosonic qubits encoded. I think that requires maybe different, I don't know, more hardware development or engineering. Yeah, I don't know. Maybe, you know, it could also be the fact that, well, okay, Shilkov works also has a company, because you say some efforts are when there involves multiple qubits, it's more of a company effort, right? And what you do in academia is just like at the 1 qubit level, you try to push it, and then the company can take it over. Yeah. I don't know. Yes.
The n cycles for the reinforcement learning.
Sorry, what?
You meant the n cycles for the reinforcement learning.
Yes. Yeah.
But then you'd only have to do it once, right? Why?
No, you repeat this cycle many times. So is that what you're saying?
Like usually,
yeah.
Whenever we calibrate it once, and that stays for like a couple of hours.
Well, but this is a QEC cycle in which you stabilize the qubit, so you keep applying this process. But you can calibrate it once. I don't actually, honestly, I don't actually know whether they do that multiple times or they change it over time. I think they do it probably once, and then they just keep applying it. But honestly, I don't know, because this is quite sort of involved compared to the earlier work in terms of how this is. But I guess they got a good, you know, very good result out of it, all this effort. Yeah.
Yeah,
yes?
I thought that the repeated layers was to stabilize the qubit, and then
yes.
you stop when you know that you achieved a certain fidelity that you want to.
No, you keep on doing this during the whole, like, you know, well, okay, this is just time. So here's they say 100 QEC cycles. So they just keep on doing this, because if it's a good stabilization thing, you should keep on doing it, right? I mean, you execute the same sequence, because it keeps you in that, it keeps the state the same. But of course, there is a chance that you prepare the 0, and during this process, somehow you turn it into 1. And that's what they record as a logical failure. Right? That you started with a 0, and at the end you have a 1, or you started with a plus, and at the end you have a minus. That's the kind of thing they're testing. And that is what this TX denotes, right? Here you start with a plus, and then there's the probability you read it out as a minus. Yeah. Yes? I hope that is sort of clear. Okay. Okay, and then I mentioned this cooling, but just in passing, but this is somewhat completely different thing. All right, so now here we are, middle of the second lecture. We're starting with the second lecture. Okay, so I will see how far we get, because at some point maybe you're through with these. I mean, the dual rail qubit is a nice idea, but it's also something that is, you know, one can talk about the ideas. Maybe I'll just have one slide on it. We'll see. Because I think the bias noise qubit is kind of cool in terms of that's been pushed to the sort of multi-qubit level a little bit by Amazon team. Okay, so the goal, let's just remind ourselves, the goal is to have a cat qubit where 0 is alpha and 1 is minus alpha. And the reason is that we expect that the bit flip error is exponentially suppressed in alpha squared. So the bigger we make alpha, the more distance these two states have in phase space. And the phase flip, though, you know, on the other hand, because of photon loss, because if we take superposition, it increases linearly with alpha squared. So we should find some value. Well, so okay, how we should conclude from this? We say, well, so we could maybe say this qubit, it already has a bit flip error rate, which is, you know, 10 to minus 4. So we don't need to have error correction on top. We're just going to correct phase flip errors. So we're going to make multiple of these cat qubits, and we're going to use a phase flip error correction code. For example, a repetition code that corrects phase flip errors. Now, while we're doing that error correction, maybe the bit flip error will increase, but maybe they'll increase to a level that, you know, these maybe are the same now, right? So maybe this started off not as 10 to the minus 4, but something 10 to the minus 1, and now we reduced it, and now this got up a little bit, so maybe both are 10 to the minus 3. I mean, I'm just throwing some numbers at it. All right. But now you say, well, okay, so what we want to realize, you say, well, is this really true? But so the way this, so okay, so people have proposed basically 2 ways to make this cat qubit. One is called a Kerr-cat qubit, and it uses a Kerr nonlinearity. So it basically tries to, it writes down a Hamiltonian such that the state alpha and minus alpha are eigenstates. And that there was an experiment, I will mention this later, that worked with that Kerr-cat thing. And this slide is on a dissipative cat, where we try to imagine a dissipative mechanism, just like we've seen for GKP, that drives any state to a superposition of alpha and minus alpha. Right? And we should understand if it's just a superposition of alpha minus alpha, it may be the wrong superposition, right? So we want to say maybe start with alpha. Maybe there's some errors happening and this dissipative mechanism pushes me back to alpha, approximately. Yeah, so we want some dynamics given by a Hamiltonian H and some Lindbladian, such that the space spanned by alpha and minus alpha is a steady space. So any superposition of alpha and minus alpha. And what Lindbladian does that? Well, this one. So L noise is some other stuff that I don't want to have. We can ignore it. It has single photon loss, maybe some dephasing, etc. But these are the terms that I actually want to have. And H skew is a squeezing term. This term is a 2-photon loss term. So I want to engineer 2-photon loss. The way to understand this, so there's 2 ways to understand it. One is actually on the next slide and could be seen as an exercise. You know, prove that this Lindblad equation has the state alpha or minus alpha as fixed points. So R dot is 0 for these 2 states. Okay. But we can also understand this slightly more intuitively, which is the following. So alpha A on the annihilation operator on alpha pulls back, you know, A on alpha is alpha alpha. Okay, this is the thing we know. So if I apply A squared, I just get this the square. So then it doesn't matter whether I have a plus or a minus. Note that, you know, a dagger does not, you know, a dagger on alpha does not, is not an eigenstate, right? So then you can say, well, maybe the way I can think about this is that I see, you know, we know, okay, so what happens when you drive, we have a driven dissipative oscillator, right? So let's forget about this 2-photon loss. What I have is I have a drive, which is A plus A dagger. Doesn't do displacement, so it drives an oscillator, puts a force on it, and then I also have photon loss. Does anybody know what is the state that I get? You know, well, okay, so it says that actually, but okay. So you get a coherent state. You get a coherent state with parameters that depends on the drive strength and it depends on the photon loss rate, right? This is very intuitive. You supply energy, you push the swing around, it decays, you get it into a steady state depending on, you know, how much pushing I keep doing. And also the phase of the drive that I put, which is, you know, related to parameters like E can be complex, that sets the, you know, it sets whether I'm stabilizing, it sets the phase of this thing. For sure, you know, this state is always sort of rotating, right? But there's a phase. If I remove this rotation, there's a certain phase because alpha is a complex number. So you can just read, in some sense, you can just read this Hamiltonian, replace A squared by A in the sense that, you know, the action of A squared is now similar as the action of A, except that it just has 2 states which are invariant, right? So instead of having a drive, which is A plus A dagger, I have A squared plus A dagger squared. And instead of having a single photon loss, I replaced it by the 2 photon loss. So I replace A by A squared. Okay, so that's a simple intuitive reason. And what I get back for it is that I now stabilize 2 states. All right, now when you get that idea, you say, oh, so maybe if I have this 4-legged cat, remember the 4-legged cat with I alpha minus I alpha? So maybe if I do this with an A to the 4th, right? So because then I have if I have A to the 4th, I get I cancel this I also, right? And indeed there is such a dissipative mechanism where I have to have some 4 photon loss. But this is of course harder to engineer potentially than just 2 photon loss. All right, now, okay, so just one slide on the math. You know, so for example, if you were to do this exercise, you could, yeah.
Sorry, what was the L noise?
Oh, that's just anything else. Yeah, I put that in. I didn't need to have that. L noise is just things I don't want. Yeah, I didn't need to have that there, but it just, yeah. All right, so if I rewrite the Lindblad equation, you know, in the Lindblad term, I always have something, you know, I have this 2 photon loss, will do something like that. But then the other parts I can kind of put into my effective non-Hermitian Hamiltonian. Some people like non-Hermitian Hamiltonian. That's where it comes from. I don't think it's extremely deep, but all right. So I can rewrite the equation like this, and I can do some math. This is in my lecture notes if you want to check that these states are fixed points of this evolution. Okay. Okay. So now. Yeah, so we can control the phase, you know, okay, so we control like if it's real alpha or alpha with some phase by setting the phase of the drive, the 2 photon drive. And we can control the amplitude by also, you know, playing with kappa and or with this drive strengths as well. Now, if I turn the drive off, I have a very simple system, because it's something that if I apply a 2 photon loss, you know, if the Fock state 0 and 1, of course, are annihilated by it, right? So if I have these 2 Fock states, then this term is 0, and this was 0 anyhow, because there's no drive. And these are clearly even and odd parity states. So if you remember, alpha plus minus alpha was an even parity state, and alpha minus alpha was an odd parity state. So what happens when I turn this drive on, if I start, say, in 0, I go to alpha plus minus alpha. If I start in 1, I go to alpha minus alpha. So I could be preparing, okay, so then you can say, okay, how am I preparing these states? Okay, if I prepare 0 or 1, I could just prepare display state alpha or minus alpha. That's simple, because I just, you know, put on a drive on this resonator and do that. And if I have to prepare alpha plus minus alpha, or the even or the odd cat, I could start with making Fock states, vacuum or single photon state, and I could gradually turn on my drive in principle. Now, of course, I have to prepare also the single photon Fock state, so I mean, you know, the point is I actually don't know, like in the recent experiment, whether this is exactly what they're doing, but they are preparing as input to their repetition code experiment, you know, these states plus and minus. So that's alpha, the even and the odd cat states, right? So they have to do something like that. All right, but then you say, of course, now how do you engineer 2 photon dissipation? And that is similar as what I said for the GKP. If I had a Hamiltonian that looks like this, and this mode C were lossy, then I could, you know, I get effectively some 2 photon loss through this interaction. But then you can say, well, how do I get this? And this is then going into sort of, you know, circuit QED kind of things, by which you know, in circuit QED, these Josephson junctions induce terms which are cosines, potentially with external potential. But if you put multiple junctions together, there's ways to get effective phi to the 3rd terms. And phi, if we go back, what it was, it's a flux, but it can be written as a linear combination of creation and annihilation operators. And so maybe these involve the mode A and the mode C and so on. And so there are ways to get terms like this, basically. Yeah, but I'm not going into that because that's a sort of that subject is like between David's and my lecture. Right. Okay, so all right, so this is a very full slide with stuff. So I want to, because like, you know, for every qubit I can mention, there's a whole wish list you can write down, and there's a lot of discussion and literature and da. And, you know, we can't cover everything. I'm just going to give you some of the basic ideas. All right, now I already mentioned, so it's not that hard to prepare. Good, right? Unlike GKP qubit, this looks a little easier. Also, the number of photons we're going to see is a little lower. Like they work with 3 photon, average number of 3 photons or 1 photon. So it's almost like I'm just, you know, working in a qubit space, you know, like in a Fock space, a Fock state with 1 photon. Okay, so the Z preparation, X preparation, I already mentioned. X measurements. So what is the X measurement? Plus or minus or the even and odd cat. So I have to measure photon parity. Okay, so that was also something that we discussed. We can measure photon parity using an select qubit in principle. Now we want to maybe rotate, right? And so we realized that so we can do single qubit rotations by having interactions like this. Yes, let me just. Yeah, this is not okay. So the point a little bit. I'm not going to cover this too much, but the one I'm actually not sure that they do this in the experiment or they need it. But in principle, you could do single qubit rotations. So the A, you know, doesn't. These states are sort of eigenstates of A, right? So they don't. They just put different phases. If I had an E to the I, some phase A, then I just get different phases. So that looks obviously like some Z rotation, right? Because, you know, Z rotations should put a different phase in front of the 0 and the 1. And the operator A, if I have that in exponent, would you know, puts an alpha and a minus alpha compared to these things. So, but A dagger does not really, you know, if I apply this, I'm not really staying in this space spanned by these even and odd cats. And this is where this dissipation also comes in. We could say, well, maybe I do some drive like that to do a rotation, and then I quickly apply my dissipation again so that I'm back, stay in the space.
But I think,
yeah.
I think this leakage is exponentially suppressed by the mod alpha square.
So the what? The leak?
This leakage might be exponentially suppressed by the mod alpha square. There is a gap in the.
Yes, yeah. I think that is what is believed, but I don't know. Okay, so maybe this is. I'm not sure. They probably did this in experiment, but I'm not 100% sure about this. Yeah. Now, okay, so single qubit X rotations, because we could go to. Yeah. So you know, if we do an X rotation, we could sort of change. Okay, no, that's actually not what I was saying. Sorry.
And I think the A gives the resonance, right? I mean, oscillation between the plus and minus states.
Yeah, but I think, okay, so what I want to say here is actually you could change the phase of the drive, and then you change, you know, what is stabilized. So you can apply any phase here. So you can map alpha onto minus alpha and these kind of things. But I think, but you know, this in practice is also more complicated. So, okay, so maybe this is a little bit sort of a, you know, kind of a short discussion. Now, when this thing was put out, a big deal was made out of doing a C0 gate that was noise bias preserving. And I want to spend a little bit of time on this noise bias because it's not, it's a discussion that can confuse, can be confusing. So what does noise bias preserving exactly mean? So if I look at a C0 gate and I have incoming errors, if they're X errors, they stay X errors. If they're Z errors, they stay Z errors. So that's not what noise bias preserving means, right? You know, if for example, if you have a control Z gate and you have an X error on one gate, then it becomes a Z error on the other. It propagates to a Z error, right? So that's not what this meant. But the point is the gates have several features and we have to be precise about what we mean. What I want, so the bottom line is basically what I want to avoid. I have bit flip errors that are exponentially, you know, suppressed. They're very low error rate. And now I want to use maybe, you know, I want to use a phase flip repetition code here. Or maybe I want to do some surface code because I will still want to correct some bit flip errors. But I never want to do a Hadamard that converts phase flip errors to bit flip errors. Because if I do such Hadamard gate, then, you know, that sort of high rate phase flip errors gets right away converted to bit flip errors, and then gone is my noise bias, right? So the Hadamard gate should be sort of out of my picture. It's a dangerous thing. But you can also, but then you say, well, the C0, for example, if I had a C0, maybe the C0, if I have it as a Hamiltonian, it needs to have something like this. If my control is a 1, I should, you know, generate some bit flipping on the other guys. And if my control is a 0, I do the identity on the target, right? But then you could say, let's say I have phase flip errors during this C0. And then I rewrite that as doing a perfect C0 and then followed by some error. Then there's no guarantee that these errors will stay phase flip errors, because, you know, stuff that is acting on this target and is Z-like may as well become X-like or is Y-like, right? So the problem is when they discuss, so there's a paper in which they come up with a noise bias. So that's what they mean by noise bias preserving, that if I have the errors during these gates, they should not come out at the end of the gate as the sort of the bad errors, as the bit flip errors, right? Yeah, so in particular, the phase flip errors are going to be sort of the, you know, the photon loss errors, say. And so you can also say, well, if I have it, let's say I build a C0 gate that's noise bias preserving, then of course I have my control Z through the Hadamard, but that's not allowed because then I had to do that Hadamard. If that's control Z0 is dominated by phase flip errors, then of course doing that Hadamard will be dominated by bit flip errors. Yeah? So this is sort of a subtle issue because you really have to, you know, see, okay, so in the end, so the company Alice and Bob, David's on the advisor board, so they are trying to, I think, build this noise bias preserving C0 between two cat qubits. And they're still working on it, but it's not an easy thing to do. Maybe, you know, wish them good luck. What is done in this recent experiment is that actually, instead of doing a C0 between two cat qubits, you take a transmon. So the whole architecture, or the whole idea is that your data qubits are these cat qubits, and the ancilla qubits that you use for error correction are transmon qubits. And of course, this idea of using different types of qubits can be, you know, advantageous. You know, transmon qubit measurements that you then use to measure error information. They're well developed and so on. Okay, so we'll have a look at that in a moment. Now, I also mentioned there is this Kerr-cat qubit. I just want to flash this Hamiltonian. So I said this Kerr-cat qubit doesn't have a stabilization mechanism, no dissipation. It just has a Hamiltonian that, again, I have to engineer out of some squeezing interaction and some Kerr nonlinearity, and that's why it's called a Kerr-cat. And this Hamiltonian, one can verify that it has the states plus and minus alpha as eigenstate. Okay. Right, okay, so now we want to move. How we're doing on time?
15 minutes.
Okay, yeah. All right, so now I want to, so I probably won't get to this dual rail qubit. Now I want to sort of give you a little bit of an idea of this this paper, which is you know, a nice paper because it's the first time where these Bosonic qubits are used in some bigger code. And so the point of the so we're going to use the phase flip code. So basically the idea is that you would prepare something like so these two states, let's say you prepare a logical, so you have 3 cat qubits, each prepared in a plus. Remember, the plus is the even cat state. And you'll be measuring, you know, let's say this is qubit 1, 2, 3. You'll be measuring x1, x2, and x2, x3. And so you do an experiment with this state, and you do an experiment with this state. You're measuring repeatedly x1, x2, and x2, x3. And you do that by coupling these qubits to a transmon qubit. And then after many cycles of error correction, you know, you have to see whether you still have this state. Or if nobody told you whether it was this state or that state, and you only get this data, can you, at the end of the day, after all these many cycles of error correction, can you figure out whether it was this or that state? That's roughly the type of setup that you do, which is done for, you know, the surface code. So what we have here is that in this experiment, we have five of this cat data qubits. And these are in coplanar resonators. So this is a chip, but we cannot point to all the structures. But it's S1 to S5, and these are all in blue. Right? So every blue structure is a coplanar resonator, which they take in one mode, and that is where I'm going to put my cat, my even or odd cat. And then in order to measure the, so if I have 2 qubits, 1 and 2, and I have my ancilla, in order to measure XX, I need to do this, so this is plus minus. So I need to prepare my transmon qubit in a plus. I need to do 2 controlled knots, and I need to measure this in the plus minus basis. So, so I'm going to be using a controlled knot between a transmon qubit and a cat qubit. And we're going to describe how this works. And so this is not so hard to understand. What this does is because, you know, what does a controlled knot do? If the qubit is 1, I should flip this, right? But what if the cat qubit, we had sort of this. So flipping it means doing a rotation from alpha to minus alpha. So what I need to do is I need to basically do a qubit controlled rotation, right? So that's, we've seen before, qubit controlled rotations. So that's these transmon qubits, you can't see them on the picture because what they actually do, so how do I do a qubit controlled rotation? I need to have a dispersive interaction. Now, in this setup, this dispersive interaction is tunable, which is nice because they can turn it off. So they turn it off, they do their dissipation stuff, and then they turn the dissipation off, and they do their qubit controlled rotation. And then they turn the dissipation on again, and that really turns out to be helpful. So this transmon qubit ancilla, you know, these Josephson junctions are very, you know, there's a lot of structures here. So it's somewhere over here because there's also a tunable coupler and da-da-da. Okay, so that's sort of what's said here. Now you see also there's some flags and stuff because there's another trick that comes in that they do. Is we've also discussed this fact that your qubit is as good as your transmon that couples to it. Well, it's not entirely true, but if you do controlled rotation and your transmon qubit decays during the gate, then you may be doing bad stuff on your Bosonic qubit, on your cat and so. So what they do is an idea, which is a fine-tuning of a dispersive shift. And this has also been done before by I think Rosenberg in the Yale group. And they say, okay, so usually the dispersive shift, you know, it's this Z A dagger A interaction. So depending on the qubit being 0 or 1, I have I rotate this way, that way. But here we the qubit can also be, it can be in 0, 1, or 2. And what they do is that they make sure, and this is, I think, do another drive, probably, I don't know the details, that the dispersive shift, if the qubit is in state 1 or in 2, is exactly the same. And it's different from 0. And then actually, instead of having this plus state, they start with 0 plus 2. So you start with 0 plus 2. So this is not their idea, it has appeared before. You start with 0 plus 4. So then if the qubit decays 2 to 1, you're still doing the right dispersive shift, right? And this is sort of a mechanism for sort of, fault tolerance, for protection or something. Now, one thing that does happen, if you do this, so if you do have this decay, and you do this, this final sort of rotation, because you say, well, how do I make this state? But okay, you can make that state on the qubit, that's fine. But you can also detect it here. You can detect whether your qubit has, basically the point is the gate that you're doing, if your qubit decays to 1, you'll not be doing the right rotation, because this measurement in 0, 1 is actually just a rotation and then measuring in 0, 1. And so if your qubit has decayed, you're not doing the right thing. And you'll be measuring, say, the state 1, because this rotation doesn't have any effect. And they can flag that. So they can know, they learn when sometimes the information they're getting is wrong, right? So then they can use that in their repetition code and say, this is these flags that tells them, ignore that information bit. This is not a measurement of XX. This is just a qubit gone to the wrong state. And then they, can study whether that improves the performance. All right, so here are some further pictures. There's a lot of pictures on this slide, but I already said some of the things in words. Okay, so qubit could be in 0, 1, or 2, ground, excited, or up. When you do the controlled knot, you prepare it into this state, superposition of 0 and 2. This is the dissipative, this 2-photon dissipation. And that's the process that I described before. And there's the controlled knot. Then you read out your qubit and you reset it, and then you go into a next QEC cycle. Right? And so the point is that with this readout, you can actually distinguish these 3 states. And this is a nice tool that we also have used at QuTech. I'll show you a picture. Now, for this dissipator, there's a lot of components for 2-photon dissipation. So there's a lot of other stuff that's going on. You see here multiple Dosum junctions, which may, create this phi to the 3rd interaction and things like that. So, okay, so now one thing is that in their case, the noise bias, when you do the C0 gates, is about 20. So the point is that the bit flip error rate is 25 smaller than the phase flip error rate, which is not a huge amount. It's not like this. Well, this is when you do these gates. Okay, so I'm maybe not being completely clear about this. Okay, so this is a picture of the. Okay, so yeah, I have to sort of decide which picture I'm going to discuss. They do verify, for example, that if you were just to leave this alone, that you get this behavior. So they have 5 qubits. And so these from light to dark are data for different qubits. Here, this is a plot. They can change the mean photon number of their stabilized qubit, like by playing with the with this dissipator and so on, which is a nice component, I think. And so the phase flip time, which is sort of the bad error, right, which is due to photon loss, goes down, right? So you shouldn't be at a too large an alpha such that the repetition code doesn't help, right? Because if your phase flip error is too high, then applying a repetition code with noise is not going to help. But they are below threshold. So they are at maximally alpha squared, I think, is 3, and going below that, and that's all below threshold for this phase flip code. Then you can also look at the bit flip time, and that is the idea, is that the bit flip time increases with alpha, right? That is this noise bias, and it should be increasing exponentially. There's a little exponent that is depicted here. All right, so now this is a discussion of basically the controlled rotation, right? Because you say, okay, now depending if I'm in the ground state, these blue things is like I'm stabilizing a cat. I'm stabilizing the state alpha. If I turn on my C0 gate, nothing's supposed to happen, right? I do a C0, and so nothing's, and then I turn it back on. Instead, if I'm in the state, 1 or 2, I have my dissipation. I turn off my dissipation, and I'm doing this rotation from alpha to minus alpha. So that's shown in the picture, and I turn on my dissipation again. Okay, so that's now you can discuss. I find it actually a little bit unclear whether their C0 is noise bias preserving. Because we said that, and they verify this, so the point is that during the C0, the likely errors, which could be, well, depending on how fast the C0 is, but they could be transmon errors, and they try to, mitigate transmon decay errors, right, by this mechanism. But it could be, photon loss errors, so there's Z errors on the cat. They should not lead to bit flip errors. So what you can do, they do repeated sequences of not C0, but Cx squared. So they actually, instead of going alpha to minus alpha, you go alpha to all the way to alpha. And then see whether, this bit flip time increasing with alpha squared is still holding. So if you just do the stabilization, it's something that we saw before. The bit flip, larger the alpha, the longer the bit flip time. And then you say, well, what if I now do, some controlled x squared, which should not do anything. And so I should be doing, if I start with alpha, I should be staying in alpha. But, is it true that sometimes I end up with minus alpha? And they look at that in terms of using the protocol with different states. For example, if you use the protocol where you don't use this higher transmon state, but just a superposition of 0 and 1, you see that this is actually much worse, right? The bit flip times are much shorter compared to just stabilization. So they say this is noise bias preserving, which in some sense is true, but it's not the noise bias on the actual cat. It's actually the noise bias that you get. It's some junk that you get from the transmon, right? And so they say that this. Well, of course, if your transmon stays in G, then of course nothing should be happening, right? So if it's in ground state, and the point is the blue line is what they effectively get, which is still a reduction, but it's better than what they. Okay. So there's some other aspects. Okay. Now maybe I want to finish with this thing. I mean, I could. So one thing I want to do maybe as a sort of looking out. So this is sort of the experiment they do, right? I have these 5, so these are all transmons, and I have 5 cat qubits, and I can compare, doing the repetition code with 3 cat qubits and 5 cat qubits, and I can see whether, I correct for phase flip errors, whether this is better or not for the bigger code, and they find it's better. But one thing you do when you repeat these measurements over time, when you repeat them, you measure x1, x2 at some point in time, and you measure it next time, and you can say, well, did its value flip? And if it flipped, I call it a defect. And that flip is telling whether errors have happened, because if I measure this x1, x2 and no errors happen, I should be measuring the same value next time I measure it. Yeah? And this is very telling. So there's our detection probabilities. So for example, you have here, depending on alpha squared. So if alpha squared is very low, if alpha squared is high, you get more of these phase flips, and it's up to 0.3, so 30%, and it's here. Now let's compare that with repetition code defect rates using transmons. And so here we are at, in between these things. Now, if you look at Google Transmon Qubit Repetition Code 2022, they had 10% defect rates. Now they have 5% defect rates, which is a lot lower than this, right? Now I can also show you the QuTech. So if we look at our experiments, for example, this was an experiment was hopefully to get better data. This is what we see in experiment for a repetition code, up to 0.4, which is, well, this is pretty terrible, right? And it goes up also. So that also shows that it's quite hard. But the point I want to make is that looking at defect rates is extremely telling what you're actually doing. I mean, there were also Chinese experiments on chip, and they had defect rates almost 50%, which which is complete garbage, right? Then it's no longer. So what this says a little bit is that that as a repetition code, they're not, this is better in some sense, right? But you have to think about this because this is they have the other error rate, which is the bit flip error rate, which mixes them up. The bit flip error rate should be a lot lower. So if we would go to a surface code and they keep the noise bias and then they're gonna benefit from that, which we don't have in transmons, right? Because there we'd say it's all about the same. So the fact that this is a little higher than what you have here should not be sort of a showstopper. But it does seem like what they're planning is to go to rectangular surface code, which is some way of saying, I have, repetition code is extreme case. I just correct phase flip errors and not bit flip errors. But in a rectangular surface code, I want to correct some bit flip errors, but they're less likely, and I want to correct more phase flip errors. Right, that is sort of, and maybe I could use transmons again. Yeah, one thing that's good is this is very steady. It's like if you saw in this data, and this is what we're seeing in experiment, and what Google has also seen in earlier installments, where this goes up, and we believe it's due to leakage. So qubits due to gates, they're starting to go to higher states. And due to, I think this is because of this dissipation in these cats, you are kind of staying in the same space. So that is maybe a good sort of take-home message from that. Yeah, well, here are some other data on these. So typically you say, okay, well, I'm, if I have a number of QEC cycles, I'm starting in an eigenstate of logical X, and this will go down, or this is actually a correlation, and this correlation will go to 0, meaning that at that point in time, the correlation is 0, I may as well be randomly choosing whether I have a plus or minus, right? And so this goes fast for if I have a large photon number, and it goes slower if I have a small photon number. And then you can also look at this. This is the logical error rate per time step, per QEC cycle. And this, the data of red and blue are sort of the DS3 experiments. With 5 qubits, you can do 2 DS3 experiments, the first 3 qubits and the last 3 qubits. They're similar, but the point is that the DS5 experiment has a lower phase flip error rate per cycle. So that says you are getting an advantage of using more cat qubits in expressing your phase error rate. And then they also look at, like, if you were to decode, if you use the erasure information, you get an advantage. And erasure, by erasure, they mean that this transmon qubit can be in a state that says, okay, you shouldn't, it just decayed, wrong information, ignore that bit. And that is informative because otherwise you're decoding, you're going to try to infer where errors have happened based on very bad information. Yeah, so that's what I said about rectangular surface code. And of course, they can also look at, if they do these cycles, these error correction cycles, they can say, oh, well, what is my, my bit flip error rate? You see here, the phase flip error rate for the purple thing, which is the larger code, is lower, right? Because I'm correcting those errors. For the bit flip error rate, the larger code is worse because I have more opportunities with 5 cat qubits. There's more opportunities for bad stuff to happen. And then the question is, you can say, well, maybe I want to be in the regime where this bit flip error rate is as similar as this phase flip error rate, because then I've sort of symmetrized the noise. I start with the noise bias and I symmetrize the noise. All right, so those are some points. Yeah, this is just some data about this in distinguishing 0, 1, and 2. This is actually just this from a experiment that we did, because I said we were going to talk about concatenating with other codes and so on. So you can read a transmon out you can try to detect whether it's 0, 1, and 2. Here are 4 transmons, and this is data that you get when you started in 0, 1, or 2. And you see that these blobs are sometimes fairly well distinguished, but there is some region in between, and sometimes they're not. Right? But you can feed this information. What you can do is you say, well, to decode, like I do a repetition code experiment, and this is not a bit, nor it's a trit. It's not 0, 1, and 2. It's one of these points here. And I can say, well, if this point is sort of right in the middle of these blobs, I know I'm not as certain that it's a 0 or 1 outcome. And again, I can use that in decoding, saying I should not be trusting that bit of information. And that's what we explored in this paper, and it's also been theoretically explored by using analog readout information. So you have sort of you sample from a Gaussian, which is centered around the 0 blob or the 1 blob or the 2 blob. And that is information that is used in decoding. We actually also use the neural network here to maybe have small improvements in decoding. But these things, come in at a different level, of course. Okay, so yeah. Okay, so now I have I think I have to stop, because there's the dual rail qubit. If you want to know more, so dual rail qubit is something where I use 2 cavities to encode 1 qubit. And I use 0, 1, or 1, 0 as my 0 and 1. And the advantage is that the photon loss will get me out of this space and say, well, that doesn't sound so good. But if I measure the photon parity, we've been doing a lot via transmon, right? So, but now I have to measure it sort of with both these things. Then I can detect photon loss. And if I have a detectable error, which has a flag I put back, so I say maybe there's a photon loss on the second mode. And I started with this state, so I now say it's not odd photon number, but even. I put it back in one of these states, and that information is useful in error correction, in principle. Okay, but I'm going to stop there, I think, or just leave some room for some questions. Yeah. Is that okay? Yeah. Well, if you want to know more, I could say more, but yeah, let's see what questions there are right now.
So when you discussed the GKP qubit, you mentioned that for 0 logical and the 1 logical were the ones with the peaks that were discussed.
Right. Mm-hmm.
When you discussed the cat qubit, there was a 0 and the 1 that had to do with the relative phase of the superposition of alpha and minus alpha.
Well, 0 was alpha and 1 was minus alpha, approximately.
Right. But now on top of this, there is the repetition code, and so the logical qubit is now 3 cats.
Exactly, yes.
So are there then, can one think about repetition codes of GKP qubits?
Yes, exactly. Yeah, thanks for the question. So yes, indeed. We have also worked on this thing, like imagine you have a GKP qubit and then on top you build the surface code, and how would you do this and so on. So you have a whole lattice of GKP qubits and so on. But then, it's just like a little early. I mean, I think it was an interesting study, and but we just play with very simple noise models. We say, well, we have mixtures of displacement as our error model, because then we can simulate this, and we can do decoding and things like that for the surface code. But I think the point is that the first question is, because what you can actually do, which was nice, is that if my GKP error, so the GKP could be stabilization, but then maybe I don't learn anything, right? It's just being stabilized. Or it could be some process where I do error correction and I learn a syndrome. So I measure SP and SQ and I find error information. That could be passed on to the surface code. Because on the surface code, you have a whole lattice of qubits. And if you know that it's more likely qubit, you know, on the left there, that's gonna go the error, that is very informative. So that's known, if you concatenate codes, you want a message pass. You want to pass messages from the underlying code to the top code to improve your error correction. And so if you have more information at your GKP error correction level, you can pass it on. But the problem is maybe also with GKP error correction, you know, if you do it via this extra GKP ancilla and then measurement, it's maybe slow, it's not so hardware efficient, right? So there's considerations like that. Yeah. But you can also do all this GKP plus surface code in this optics things where you do it measurement based. So you don't have to have it stationary with cavities. So there's people working on that as well. Yeah. Okay. Yes.
So since you brought up this measurement with the qubit, right? So the GKP also the readout or the stabilization, let's say, is through a qubit, but so also for this kind of a cat.
Yeah, but the cat is not like, okay, so the cat stabilization is not, there's no explicit, well, okay, so if I do the control knot, the transmon measures the repetition code checks. But the stabilization of this thing is, that's just purely a path. There's this buffer thing, right, which is the green stuff. Well, there's the, there's the buffer mode and so on. So that, and there's maybe, I mean, you know, there's other lines and stuff, but there's no information coming out of that. Yeah, or not used. Yeah.
I know you didn't talk about squeezing, but given that it's the higher alpha that really causes damage for the cats, then is that why people think about the squeezed cats? So that
Yeah, exactly. Yes, indeed. But I think in this thing, they haven't used that yet. I guess they could, or I don't know what it would take to integrate that. To have a squeezed cat. You know, the question is also whether the gates, maybe that's okay. It's a controlled rotation, but then the squeeze changes direction, but maybe it's okay. Yeah.
Finally, do you think the noise bias is an advantage or not?
Well, okay, so maybe I didn't say this so clearly indeed, that the noise bias has been announced as an advantage because it leads to less overhead. Because you say, well, I have this very hardware efficient way of encoding, and I just make a bit, basically, something that is a very stable bit in one cavity. And then 0 and 1 are not likely to go into each other. And then I only need something like a repetition code. I need correct one type of errors, and and that is less overhead intensive. But I think that is a little too, too ideal, right? So these ideas, they are launched like, oh, this is going to be it. Oh, no, okay, we have to, But I mean, and then something remains because they're going to use rectangular surface codes, perhaps. So there is still, there's still opportunity for benefiting from this bias. But I think this C0, that you have to have a very advanced, because you say, well, maybe I can do this for the transmon too. But to come up with this C0 gate that preserves this noise bias is not that simple. So, that's the question. Can you preserve the noise bias? Because there's other means to deal with noise bias, because that's also natural. Like if you have a qubit, there's often much more dephasing as decay. But then you say, yeah, but then I do the Hadamard gate. So I need a scheme where I just have maybe Z rotations and control Zs. And so they just have a high dephasing rate. And we've actually worked on this kind of thing, also John Preskill and so on. It's not that easy, so yeah. Does that answer your question? So
Yeah, so I guess in a way it puts the burden on the logical operations that you do, or even how you implement the logical operations. So it seems like something's bad. Like
Yeah, I think it's definitely an interesting thing to pursue, but and also, you know, you can do repetition code, but Aldous and Bob had this paper where you don't want to, the repetition code is not so efficient. You code one logical qubits in like, you know, D. You can use more efficient codes in 2D, and that you would not be able to do in 2D if it just, you have to correct both in X and Z errors. So that's sort of potentially interesting. But you know, at the bottom line, first you want to show you're below threshold of some code. And yeah, so I guess it's like, maybe in 10 years we'll know whether it was a good idea or, yeah. It's definitely, you know, I think it's a lot of creativity that goes into these ideas and then trying to make them, you know, in the lab and so on. So.
No further questions, and let's thank Professor Barbara again.